Theories of the past can predict the future. Stephen Hawking explains to the reader that a theory is a model that accurately explains the observations around us. The most widely held theory is supported by consistent results from multiple experiments. These theories explain how and why things happen around us. Dr. Hawking offers two of his advantages related to the development of the theory. Theories provide the basis for scientists to predict future events. Dr. Hawking provides an example of Newton's theory of universal gravitation. This theory allowed scientists to predict the future movements of the planets. Theories are never fully integrated. This means it can be continuously improved as more evidence emerges. This refutableness is very important for the development of our knowledge. Scientific theories allow us to infer the nature of the future universe. However, it is constantly evolving and becoming more and more accurate at predicting the future. Newton's theory of gravitation greatly enhances our understanding. Newton's theory of gravitation is revolutionary. In the 17th century, it was believed that objects were at absolute rest naturally. Therefore, without any action, the object will remain motionless. Newton reversed this idea by proposing that all objects in the universe are in constant motion. This theory is supported by Newton's observations of the planets continuously moving relative to each other. Newton's three laws. Based on Newton's discoveries, he developed three laws. All objects will continue to move in a straight line if no other force is applied. An object accelerates with a velocity proportional to the force acting on it. Also, the greater the mass of an object, the less force is exerted on its motion. All objects in the universe attract other objects with a force proportional to each object's mass. The speed of light challenges Newton's theory. When we are in constant motion relative to other bodies, Newton described speed relative to other bodies. However, Hawking explains that our understanding of the speed of light has challenged this part of Newton's theory. The speed of light should always be constant, not relative. It's still 186,000 miles per second. The solution to this gap in Newton's theory was solved in the early 20th century by Albert Einstein. Specifically, Einstein's theory of relativity. Time is not fixed. The theory of relativity is based on Newton's theory of gravitation, which takes the speed of light as a constant. Einstein suggested that the laws of science are the same for all freely moving observers. This explains the constancy of the speed of light. Regardless of the speed of a freely moving observer, the speed of light will be the same. The rationale behind this principle is that time is relative, not fixed. Hawking uses analogy to explain this point. Imagine that a ray of light is emitted towards two observers. One of these observers moves towards the light while the other moves faster in the opposite direction. The speed of light is constant for each observer because it is constant. However, time is determined by distance traveled divided by speed. Therefore, two observers will perceive the light emitted at different times. Crucially, that means that no observer will ever misrecord the first time the light was emitted. Instead, time will be relative and unique to each observer. Quantum states help us measure particles. All matter is made up of particles. Therefore, to better understand the universe, we need to understand particles, including their behavior and speed. However, particles are particularly difficult to measure, Hawking explains. The more accurately you try to measure the position of a particle, the more uncertain its speed becomes. Likewise, the more accurately you try to measure its velocity, the less precise the position of the particle becomes. This phenomenon was discovered in the 1920s and is known as the uncertainty principle. To overcome the limitations of particle measurement, scientists began to measure the quantum state of particles. The quantum state combines the many possible positions and velocities of a particle. Therefore, it is currently not possible for a scientist to accurately observe the position and velocity of the particle. Instead, the scientist needs to keep track of all the places he might go and figure out which ones are most likely. The variety of places a particle can appear can be represented as a wave that looks like a continuously oscillating wave. The most likely positions of the grain occur when the arcs and valleys are aligned. Massive objects bend spacetime, causing gravity. Hawking explains that the gravity of massive objects causes spacetime to warp. In addition, massive masses like our Sun alter spacetime. Imagine the spacetime analogy as a blanket stretched and held in the air. If you place an object in the center of the blanket will bend and the object will sink. Once this curve is created, other objects will follow these curves in spacetime. Hawking explains that this is because an object always takes the shortest path between 2 points. With larger objects, it is a circular orbit. Spacetime is the fourth dimension of our world. Physicists use spacetime to describe events in the universe. For these scientists, an event occurs at a specific location in space and time. Scientists have to consider time because relativity says that time is relative. It is then an essential element in describing the nature of an event. Essentially, our understanding of spacetime allowed us to develop a theory of gravity. Collapsed stars can create black holes. Stars depend on enormous amounts of energy to produce heat and light. Also, since they usually have a long shelf life, this amount will accumulate. Once this energy is exhausted, the star will die. The size of the star will then determine the product of that star's death. For example, massive stars create black holes. Hawking explains why the death of massive stars can create black holes. Black holes are created from these events because the gravity of massive stars is so strong. Stars use their energy to keep them from collapsing due to strong gravity. However, once the star runs out of energy, it begins to collapse on its own. All surrounding matter is pulled inward towards an infinitely dense spherical point called a singularity. This singularity is what we call a black hole. The attraction of a black hole is so strong that light is bent along it. In addition, its strong gravity prevents anything that crosses a particular boundary around it from escaping again. Hawking notes that this point of no return is called the event horizon. Light is the fastest moving thing in the universe. However, even light cannot escape from a black hole. Since light cannot escape from black holes, this highlights the dilemma of observing them. However, scientists are studying the gravitational effects on the universe and the X-rays produced when the black hole sucks in and tears apart matter. Time can only pass. Hawking explains in A Brief History of Time that the expansion of the universe allows time to move forward. However, some scientists have not yet given up on the possibility that the universe will begin to shrink and time will begin to turn back. Even so, Hawking argues that there are some strong indications that time can only move forward. Arrows of time. The second law of thermodynamics is called entropy. Entropy suggests that disorder tends to increase over time. The disorder often does not spontaneously rearrange itself, suggesting that time can only move forward. For example, a broken cup will not spontaneously rearrange. It is the thermodynamic arrow of time. In the same way, you will form the memory of that broken cup. However, before this event, you will not be able to remember its future location on the ground. It is the psychological arrow of time. Finally, the cosmic arrow of time refers to the expansion of the universe. As the universe expands, entropy increases. Suppose the disorder in the universe reaches its maximum point. In this case, the universe could begin to shrink, reversing the cosmic arrow of time. We won't know, though, because intelligent beings can only survive as anarchy increases. This is because we rely on entropy to break down food into energy. Then time could turn back one day. However, we won't be there to see it. 4 fundamental forces. Gravity is one of the fundamental forces of the universe. However, Hawking describes 3 other fundamental forces of the universe. Electromagnetism. Electromagnetic force can be observed on all charged particles. This includes electrons and quarks. Furthermore, these forces produce events like magnets sticking to the refrigerator. These forces can be attractive or repulsive. The attraction occurs between positively and negatively charged particles. In contrast, repulsion occurs when 2 particles with the same charge meet. Hawking showed that this force is much stronger than gravity and affects even the tiniest atoms. Weak nuclear force. The weak nuclear force acts on all the particles that make up matter. This force is considered weak because it can only apply force over short distances. The nuclear force produces radiation. At higher energies, the strength of the weak nuclear force increases until it equals the electromagnetic force. Strong nuclear force. This nuclear force can bind protons and neutrons in the nucleus of an atom. Likewise, it can bind small quarks in protons and neutrons. The strong nuclear force is different from the weak nuclear force because it weakens at higher energies. Great unification energy. There is a state of high energy known as the Great Unified Energy. This state occurs when the 3 forces reach equal strength. In doing so, they become different aspects of the same force. Hawking suggests that this unifying force may have played an important role in the creation of our universe. How did the Big Bang happen? Scientists almost completely agree that the Big Bang happened. What many scientists disagree on, however, is how the Big Bang happened. However, there are 2 important theories about how the Big Bang might have happened. Hot Big Bang model: the universe began at 0 size and was extremely hot and dense. The Big Bang causes expansion, which then lowers the temperature of the universe. The reason for this cooling is more widespread heat. During the first hours of this expansion, most of the universe's current elements were created. The largest objects in the universe began to rotate due to gravity, creating galaxies. Then, clouds of hydrogen and helium gas began to collapse inside these galaxies. This collapse, along with the collision of atoms, created nuclear fusion. These reactions are the source of the stars. The death and collapse of these stars created massive stellar explosions that ejected more elements into the universe. These elements helped create more stars and planets. Inflation model: the energy of the early universe was so high that the 3 forces above were equal in strength. With the expansion of the universe, these 3 forces have developed different forces. It happened quickly. With the division of force into force, a huge source of energy was released. The release of energy produces an anti-gravity effect. Anti-gravity effect causes the universe to expand faster. Conclusion: if there really is a complete unified theory that governs everything, it probably also determines your actions. But it does so in a way that is incalculable for a creature as complex as a human. The reason we say people have free will is because we can't predict what they will do.